uh, I am describing MSc first year course and relativistic Lagrangians and Hamiltonian equations. Uh, First study the relativistic Lagrangians equations. In classical mechanics, the Lagrangians is defined as L is equal to T minus V. T is a kinetic energy, V is a potential energy. Where T is a kinetic of the system, T is a kinetic of the system and is functions of generalized momenta of the functions is of the generalized momenta. Okay. V is a potential energy. Okay, in the generalized coordinate. We know that classical mechanics. Generalized coordinate PR is equal to del L divided by del Q point R. This is generalized velocity. This is a del Q R is a generalized velocity. Okay, generalized velocity, and this is equal to, and this put here, this value L is equal to T minus V. T is the kinetic energy of the system and V is the potential energy of the system. Okay, this is a classical Lagrangian, relativistic classical Lagrangian mechanics. Okay, and now put here this value and del T minus V divided by del Q dash R. This is generalized velocity, and it multiply by del and del T divided by Q R dash R minus dV divided by QR. This put here, this value is 0 and this is a 0. Value potential energy is not as system is dependent vector, and this is value 0 and this is value and del T divided by del Q dash R. This is a kinetic energy. This is a generalized velocity. Generalized velocity is very important fact, and this the first equations and the second equations and second equations and since this value is 0 and since value is 0 and this value del divided by del QR, this is 0 value and the put here 0 and this final equations and this since is equal to 0. Okay, becomes potential does not depends on the generalized coordinate. Potentials does not depends on the generalized coordinate. Becomes 0, does not depends on the generalized coordinate. Okay, but only depends on the kinetic energy of the generalized coordinate. It is not depends on the potential, but only depends on the kinetic energy of the generalized coordinate of the system. Okay, generalized velocity. Okay, and this differentiate the time with respect to time and this generalized del t divided by qr, and this all respect to differentiate in the time, and del pr divided by del t equal to, and this common, and this multiply by both sides and with respect to time, and del and d divided by d and del t in this bracket del t divided by del qr, and this is a generalized coordinate, and this equation is third, and this the first equation has given, this equation is third. Okay. But according to Lagrangian equations, and del divided by del t and del L divided by q dash r is equal to del L divided by del r. This equations Lagrangian equations, and this equal to Lagrangian equations, Lagrangians per unit divided per unit the generalized coordinate is equal to derivative d divided by del t or del L divided by something. Okay. And the same bird, and this is the same bird. Okay. And equations 3 becomes and equations 3 becomes this equations. Okay, this equations 3 becomes, and this equal to same. Okay, this equal to same, and this equal to same. This terms and this term is equal to these terms. Pr divided by t equal to del L divided by del qr. Okay, and equations number 4. Okay, equations number 4, and define we have same that the time relativistic kinetic energy of particles of rest mass m naught, and this is represented the rest mass is m naught, and moving with a velocity given by, and this equations is a kinetic energy equal to m minus m naught c square, m minus m naught. This equations is the rest mass equations, but Einstein very famous equations is equal to mc square. Mc square is not rest mass the ballad, but only for this ballad of the mass energy equations relations. This relations ballad of the kinetic terms, but the depends this equations is ballad of rest mass energy in the particles. Okay, and these equations terms, but we know that m is equal to m naught under root 1 minus b square c square. This is a rest mass equations. The rest mass equations is a very famous equations. M is equal to m naught divided by 1 minus b square c square, and this equations is written, and this m naught c square is common, and aim this value, and m naught under root 1 minus b square c square. So this is relations. This is first the 5 equations kinetic energy total rest mass kinetic energy in this term, and relativistic momenta, and we know that the classical momentum is equal to p equal to mv. M becomes mass, and v becomes velocity, and velocity of particles. M becomes the velocity of mass particles of mass become velocity of particles. And relativistic momentum, this formula is equal to m naught v divided by 1 minus v square c square in the equation 6. Okay, okay, equations 6. Y definitions, the x coordinate and px and y coordinate y. Okay, this the first equation is defined as the kinetic energy is the depends on the generalized coordinate, but potential energy is not depends on the generalized coordinate. The okay, that this value is px and this value is py, and the three-dimensional terms, the y definitions of the three-dimensional terms of the equations number 7. We see that by the actual differentiations of the equations 5 is formed that differentials form that it formed at the five equations, and del t divided by del x point and something. Okay, and by definitions of the actual differentiations of the equations, the actually differentiation of equations, but do not give the respect to relativistic momentum and the components component. Do not give the relativistic momentum components. Do not give the relativistic momentum component, and the px is equal to m naught. M naught is a rest mass. M naught is a rest mass of the particle. Rest mass of the particles, and final equals to, and t star divided by x, component and y component, and m naught y divided by 1 minus b square c square is equal to t star divided by ty, and something similarly the pz m naught j divided by 1 minus b square c square equal to t del t star divided by del. Okay, and this three-dimensional coordinate. Okay, the define, and here the t star denote a function such that when the differentiated with respect to x, y, z, and t star is denotes the function such that the differentiated with respect to x, y, z, x dash, y dash, and or z dash will give px, py, pz. Okay, this function is respect to differentiate x, y, z code component. As kinetic energy, and t star is function of the velocity component x, y, z, that is the velocity component. This is the velocity component, and derivative form, this is the derivative form. The velocity component, this is the derivative form, the x derivative, y derivative, z derivative, and velocity, and this function the x, y, z, and t star equal to t star bracket x derivative, y derivative, z derivative, and this is equal to x del t star divided by x derivative t. This is a very famous terms, the Einstein convergence relations. In the next topic, I am starting the Einstein convergence relations is very famous in this general relativity, but this explanations of these terms, and this is equal to, and this is equal to, okay, and this is very famous terms. Okay, and del t star divided by del x star derivative, and del x plus del t star divided by into del y dy, sorry dy plus del t okay. And this put here is value uh, uh, okay, and this put here this value of and m naught, this is a kinetic energy, but m naught is equal to 1 minus b square c square. The x derivative dx derivative y is something like that, and this relation, and x and x derivative, x component, y component, and z component, velocity component, but actually velocity component, x velocity component, y velocity component, and z velocity component in the form from equations okay, from equations 5. But velocity square is equal to derivative x square plus y square plus z square, and differentiate the both side, and 2 vdv is equal to 2x dx, 2y dy, 2y dz, and 2 is a common, so this cancel, 2 is common, cancels, and v equal to dv x dx plus y dy plus z dz. And this put here this equation, and this equation, this putting here, and m naught vdv divided by 1 minus v square by c square. And kinetic energy, change in kinetic energy only depends on the velocity component, only the change of kinetic energy only depends on the velocity component, and dv, and v is a constant, but dv is a variable terms, and this relations t star directed to dv. Okay, this is a constant value, m naught is a constant, but this is a depend. It's a very interesting fact. Substituting 1 minus b square by c square equal to t, and the differentiate the both side with respect to dv. Okay, this 2 dv in respect to 2 minus 1 is 0 minus, and 2 is respecting to 2 dv, but t and dt. Okay, this equation, and this final vdv is equal to 1 minus c square by 2 and dv. Okay, and this is a okay, and this equations 10 given by equations 10 is given by, and dt star is equal to minus m naught c square by 2 into dt divided by t or half 1 by 2. Equations 10 is given by equation is 10 is given by, and t is equal to m naught v dv divided by 1 minus v square c square, and this 10 is given by in the form the 10, substituting here this value, and substitute this value is the minus 1 m naught c square divided by 2 into dt divided by t 1 by 2. Okay, and 1 by the differentiate the integrate we get the both side integrations and dt square and dt stars is equal to, and this terms is constant, and this is terms variables in the integrate, and this final integrations value is equal to minus m naught c square plus into t 1 by 2 plus a is a constant, with a is the integration constant, as integration constant is lasting, and this final terms is equal to minus m naught c square and under square root 1 minus b square c square plus a, and minus okay, this terms and t equal to 1 minus b square by c square, and this putting this value here, and putting this value the putting this value as 1 plus itna something, writing the equations that t equal to 1 minus b square by c square. We know that we very see v is very small, and classical terms is t star equal to 1 by half m naught v square is the kinetic energy. Equations 11, and this equations 11 and t star is equal to 1 by 2 m naught v square, and v is less than c, v is greater than c. So this equations 11 is equal to 1 by 2 m naught v square equal to minus m naught c square by a, and a is value find, and this minus terms is plus, rest mass is 0, and a is equal to is all terms is 0 approximately 0. A is equal to m naught c square. M naught is a rest mass c square, rest mass energy equations. A is equal to m naught, this constant terms. Substituting this value of a is equations 11 means the substitute the t star equal to m minus m naught c square under root 1 minus b square by c square plus m naught c square. A is this putting here this value is the equation, and this equation 11th, this equation a is the putting value, and this equal to m naught c square the final, and this curly bracket 1 minus under root of 1 minus b square by c square, equations number 12. And the next terms, the relativistic Lagrangian functions. The relativistic Lagrangian functions, the classical functions, L is equal to t star minus v. T star is a kinetic energy of a generalized velocity component, and v is v being the potential energy. Okay, L is equal to t. This value is a substitute in this form, and m naught c square bracket minus 1 under root 1 minus b square c square minus b, equation 13. Now we write the Lagrangian form of the relativistic equations of the motions, and belongs to classical equations from 12 and 13 we uses. And 12 and 13 is the relations the after terms the describing up, and this equation the 14, the relativistic form of equations 4, and this is a 14 equations, and in terms of the component, and this equations the component terms, and this putting here, and with respect to time, and this m naught x divided x with the generalized velocity component, and x or something root 1 minus b square equal to minus dv upon dt dx. This x and this L is value is putting here, and this putting here, and the x component, okay, and y component and z component, the equations 15. The relativistic Hamiltonians, the relativistic Hamiltonian functions is defined as and h equal to the summation px x minus L. Px is a component, x component, y component, and z component. This is the summation terms, the x, y, and z component. This terms uses in the summations in this form, and summation and del star divided by del x, x minus L something, and this is equations. This L is represented is something left side in the L terms minus m naught c square 1 minus under root 1 minus b square plus c square plus c. Substituting the t here this value, calculating after the calculating the t here, and del x m naught c square 1 minus under root square root 1 minus b square by c square x minus m naught c square. This final terms 1 minus under root 1 minus b square by c square, and Hamiltonian relativistic form, and this is terms after, and m naught c square, this is common, m naught c square is common, del x minus under root 1 minus x square, b square is equal to x square plus y square plus z square, and this is putting a value in this putting here under root of x minus something, and under root 1 minus b square by c square plus something, right equations, and this is bracket under 1 minus b m naught b square under root 1 minus b square by c square minus m naught c square bracket 1 minus under root 1 minus b square by c square plus v, and m naught, the final terms of the m naught x square, b is equal to this, putting here v is equal to b square is equal to a square plus y square plus z square not 1 minus b square by c square minus m naught c square 1 minus b square by c square plus v. Okay, and this is a final term in this form, and this is form the equation, and m naught c square is common, and v square is this is a common with the v square by c square, this is a v square by c square under root 1 minus b square by c square minus 1 plus under root 1 minus b square by c square plus v, and this is a cancel out, this value is a plus e, and this is a h equal to m naught c square and 1 by root 1 minus b square by c square minus 1 plus. Okay, this is cancelled by equation 7. This is the Hamiltonian relativistic function clearly. This is the Hamiltonian relativistic function. But Lagrangian relativistic function and L is equal to t star minus v, but Hamiltonian is equal t star plus b. H is the relativistic, H is the very dependency, is the modern form of the Hamiltonian relativistic functions. The classical forms L is equal to t star minus v, and modern form t star plus b. T the relativistic kinetic energy, t become t star become relativistic kinetic energy of v becomes potential energy. This form is the very interesting form. The relativistic terms is this plus, and these are the likely classical Hamiltonians also denote to the total energy of the system, and the px, py, p's are the three terms in the form, and the adding three terms p square x plus b by. Okay, and this is a final equations, and this is adding here. Okay, and this is adding here. Okay, the p square at p square, and this is a plus, this is a plus is equal to m naught b square plus c square, and the both squaring both sides, and this putting here the squaring both sides. The central equation number 18, and the substituting this 1 minus b square, substituting this the 1 minus b square, so this equation substitute and these equations is substituted the squaring and these equations, and p x component, y component, and z component plus m square not c square and m naught square by c square into c square. And substituting the expressions from the relativistic Hamiltonians in the 17 equations. The expressions for the relativistic, the 17 equations, the 17 equations is defined as h equal to m naught c square square root 1 minus 1 by v square by c square minus 1 plus v, and this equations is represented by and 1 minus v square by c square, and this putting here this equal to value, and this is a cancel, and the L is equal to c and root 1 as p x component, by component, z component plus m naught c m naught square c square minus m naught c square plus v. These expressions relate to the expressions of the relativistic Hamiltonians. This is the relativistic Hamiltonians, but the final result of relativistic form and Hamiltonian is equal to plus v is a relativistic relativistic form of kinetic energy, but Lagrangian form T star minus v is very different from the classical terms. Thank you. Okay, that's solve.